a breadth-first search to figure out a promising node to follow. And then we prune out non-promising nodes. And the way we decide is, at the beginning, we determine a bound. Bound, we will see what the bound means in a second. What do I mean by a bound, right? Branch and bound. Now, what is the bound part is what I'm trying to explain through an example. Okay? So at every step when we are selecting the node, we will figure out, hey, the solution that is going to come with that, is that better than what we already have? If it is better, then we follow that. We say it's a promising node. If it is not, then we mark it as non-promising node. Okay? So to kind of give you a better sense of what we mean by bound, I'm showing you an example here on capital budgeting. Okay? I don't know if you remember this or not. We actually did a variation of this in one of the classes. I gave that as an assignment, if you recall. Okay? So we are coming back to that example. Okay? So what is the example here? I was just preparing some Word document for you to post it in the community. I'll do that after the class. But look at it this one, right? It says we want to invest $14,000. The example says we want to invest $14,000. Okay? Now to invest, this is something that every student understands, right? You have some money, your mom and dad gave you some money and you want to invest. What? Okay, Sriprakash cannot hear me, but others are able to hear me, universal and all. They just put it in that we have 14,000 to, I call it dollars, obviously, since I'm in US. And then there are 4 investment opportunities, okay? At the end of this example, what you will understand is the concept of the bound, okay? That is why we are considering this example, okay? What are the 4 that are there? You have investment 1 requires 5,000 investment, and the value of that investment, okay, is 8,000. Okay, but how you get that 8,000? Okay, PVP Siddhartha cannot hear. What is that? And present value. They call it net present value based on the future returns. Okay? If you're a commerce graduate, you understand those kinds of things. But just assume that if I put 5,000, it's going to be worth 8,000. Investment 2, if I put 7,000, the value when I eventually get would be 11,000. Okay? Think of it as eventual value. Okay? Investment 3 is 4,000 with a value of 6,000. Investment 4 requires 3,000, a value of 4,000. So you have 4 investments, 4 benefits. Benefits meaning what is the value going to be, okay? The question then is, how do I distribute my 14,000 to maximize our present value? Okay? That is the question. Here is a case where we can show what we mean by a bound. Okay. So since we are all like we know math, this is a linear programming problem, right? In a sense. Okay. You have a bunch of variables. We declare variables, right? And then we try to come up with an equation. Okay. Ignore part of the things for linear programming, integer programming. I don't know in which class you learn these things. Typical math classes, you learn some of these things. Integer programming basically means that all the variables, they can only have values which are integers. Whatever variables that are there. It does not allow for fractional. Okay? It only takes integers. Okay? And also in this case, particular case, the integer value, when you declare the variables, are going to be assigned 0 and 1. Okay, and the way the 0 and 1 are assigned, you can see here when you look at the variable x with a subscript j, how do you interpret that? Okay. You say we'll make investment J in that variable X. Okay. If it is 0 means we'll not make the investment. And if it is 1 means we make the investment. Okay. Now, how do you read the 8x1, 11x, 6x3, and 4x4? Let's look at that. Okay. So we all understand the subscripts. Remember, xj is the investment thing. X1 is investment 1, X2 is investment 2, X3 is investment 3, and X4 is investment 4. That's how you read X1, 2, 3, 4. Anyone has questions on that? Put it in the chat. Okay? Because I have 4 investments, right? So I need 4 variables, X1, X2, X3, and X4. Okay? Now, where did the 8 come from there? 8 is, if you look at go back to line 2 in the Word document. Investment 1 requires an investment of 5,000 and the present value of 8,000. So that 8 came from that 8,000. Okay? 1,000 is a common factor. You add the 1,000 at the end, but 8 came from there. So investment 1, you are looking at the value as a present value. The 8 is that present value. So 8x1. If you look at the second investment, again line 3, that is 11,000. That is 11, right? 11x2. Third one, value is 6,000. So 6x3. Fourth one, value is 4,000. You get 4x4. So that is the equation that we want to maximize. Okay. Now, what is subject to? That is where we get to the bound. Okay. The bound is, because you don't have infinite money, right? All the investments that you do, if you look at the next one, subject to 5x1, where is the 5 coming from? 5 is the investment amount into that investment x1. So that 5 came from there. Similarly, investment 2 requires 7,000. The 7 came from there. That is your actual money that you're investing. So if you look at those things, 5x1 plus 7x2 plus 4x3 plus 3x4, the total amount invested should be less than or equal to 14. You cannot spend more than what you have. That is what that says, right? Okay. And you can see where xj is, when you say xj, what is the value of investment? We said that because we are going to say, hey, if I have invested, it is 1. If I have not invested, it is 0. That's how we are showing the investment. So xj, the values of xj show 0 and 1. And the j subscript is the 4 investment. That's why you have 1 through 4. Okay. So that is basically what we will be, what we come up with, an equation and then the bound. Okay. And if you go on further, you can see that investment 1 is the best choice. Okay. So when you say x1 equal to 1, x2 equal to 1, in the case of linear programming, where we did not put the constraint of integer value only, because linear programming, you can have fractional values. So what he's showing is if x1 equal to 1, meaning you invested in investment 1, so x2 equal to 1 means you invested in investment 2. Okay, in x3 you invested only 0.5, a fraction of the money, and x4 equal to 0. If you solve that equation, you will get a total value of, because you're substituting x1, x2, 1, 1, 6 times 0.5 in that maximize, right? Because you invested fractionally. And then, of course, x4 is 0. If you add the sum total of those things, you get $22,000. Okay? It's not an integral solution. Okay? So if you apply integer programming, by the way, you might ask me why we have to use integer programming, why not linear programming? Kind of like out of scope discussion for this class. There's a lot of reasons why we do integer programming from a computational viewpoint, faster analysis and things like that. Okay. we can always talk about that outside the class, if you will. Differences between linear and integer programming. So when you do the integer programming, where you cannot do fractional, that means in the above case you make x3 equal to 0, right? You get a value, and that value is what 19,000. Okay, that's what you are coming up with. But if you change it slightly, where you're not investing in x1, meaning you make x1 equal to 0, and then you invest in x2, x3, and x4, you're still within the bounds of $14,000, and then you get a value of 21,000. Okay? So you see how we are, what does this example show? We have some objective function. Okay? And then we also have a bound that we have to consider at every stage of the game. The investment example shows the bound in this case is how much money you have to invest, right? So at every step of the way when you're trying to solve the problem, you're always ensuring that you're within the bounds, less than or equal to. That's not the only bound, right? If you go on further to read the article, I'm going to post it in community, as I mentioned. You can put a lot of other constraints too. Bound means constraint, right? That's what it is. If you another term for bound is what are the various constraints, subject to what constraints, right? We can only make 2 investments, right? If investment 2 is made, investment 4 must be made. See, so many constraints we put in on the problem, taking the baseline problem. So you put all the equations like that and then you solve it. Okay. I was just adding notes about how you use that. It turns out that example that I gave you of capital budgeting is also a knapsack problem. In computer science, we call it knapsacking. In economics, we're calling it budgeting problem. And when we implement it, the economist on the team is coming and giving you that. And then you as a computer science guy says, this budgeting problem is nothing but a knapsack problem. Right? And what does knapsack say? Remember, we said the thief can steal stuff. And when he steals stuff, every item has a value. Correct? That's what knapsack problem is. And then the knapsack can only hold a certain weight. So what is that weight in this case? Right? So what you have is only 14. You can't exceed 14. That is a knapsack problem. So we transpose that budgeting problem into a knapsack problem, right? Where the capacity now is 14 because that's how much money we have. And then how do we invest in these 4 items? Meaning which are the items that you are going to fill up with your investment portfolio, right? That becomes a knapsack problem, you solve it. So we have a bound, right? And then you're branching off into different investments. So branch and bound means this is what it is. So to come up with that bound is how we have to figure out at every step to begin with, to solve it using branch and bound. I can, if I have to, without even showing anything, right? If I have to now extend my imagination in the brain to solving a traveling salesman's problem. Remember, that's where I stopped and switched over to this one, right? Let's say, same thing, we go back to the example that we had earlier when we considered TSP. TSP is traveling salesman's problem, right? Like Chakravarti Garu makes trips to all these colleges, right? So what is he is the traveling salesman or the coordinator, TC. What is the optimal way of covering all these cities in the least amount of time, right? And coming back to Jntuk Kakinada. That is a traveling salesman problem. What could be some of the bounds or constraints the problem could have? I mean, you can think about it. I can think about some constraints, right? So constraint could be like it is It is not the distance, but it is the cost. Okay. So I say that the cost from going from one place to other place, he should always look at the cheapest option. Hey, if he has to fly, that takes a higher cost, shorter distance, or whatever the case may be, right? Oftentimes, it's not just the actual distance, right? It is how much it costs to go there. Okay, it's not always the shortest distance. It could be shortest time. That could be the bound, and then lowest cost could be the other bound. Meaning, hey, cost is low, but it is going to take longer for me to go there. So what is it that you're optimizing, and what is that bound value you have to determine? Okay, it's called getting your bang for the buck, right? Okay, so that was the word thing. I'm putting some additional notes there for you guys to look at. Once I finish that, I'll post that. Okay, now let's go back to the slide deck. Okay, so here is let me put it back in the presentation mode. Traveling salesman problem. How we do that, right? So what does the chart show? It shows a bunch of nodes, cities, you can call it. Okay. I remember when I was teaching this, I think we had some difficulty. Somewhere I think we had difficulty understanding how the table is created. Let's try to understand the table first. Okay. So what do we have here? We have the distance between each pair of cities. Okay. With the value distance AB equal to distance BA. Okay, so how do I read this? A to A, of course, there is no distance, zero distance. And A to B is 4. The way you read it, A, B, C, D, all the way you draw a table, right? A to C is 7. Okay, this is all pairs, right? Remember we did the all pairs shortest path problem. So you already know all the pairs here. Now, how many of you have looked at a train timetable? If any one of you goes to the Indian Railways timetable and the distances between the cities, this is how the table is drawn there. By the way, here we are taking it abstractly, but think of it as distance between the cities. Okay, so if you look at A to B, it shows 4. Whereas if you come to row B, and if you look at B to A, okay, it shows 8. Is that incorrect or correct? So what it basically says is going from A to B, if you take 4 units or 4 miles, okay? Whereas from B to A, it's 8. That means they don't have to be equal. Is it possible? It is possible, right? Can you give me an example why it is possible? Is it a head-scratching question for you? You say, hey, from JNTU, Kakinada to Vijayanagaram, if it is 100 miles, coming back from Vijayanagaram to Kakinada should also be 100 miles, right? That is the common sense thinking, right? But imagine you're doing this as in let's say in the city like Hyderabad, I don't know about Kakinada, where a courier, remember we have all the same day courier service and all that, right? He has to drop off packets in different locations within the city, and they have to optimize their route. Now we do know that some of the routes are single, right, one way. Right? If it's a one way, then going from A to B might be shorter, but coming back from B to A, you can't come back the streets to come back to the destination, right? That will add up to the distance. So that is the reason why we said distance AB is not necessarily equal to distance BA. Each of them would be distinct. Okay. Let me go to the next slide. Let me pause here. Any questions so far? Everybody silent. We have the matrix. Okay. So you're using the greedy method to find an initial candidate tour. Okay. So, and we have done this too, right? We said we take the lowest value, and then so you're starting at A, we need to have a starting point, right? You look at B, C, D, E, F. Remember, you can draw this as a tree also, right? You say, okay, from A, if I look at the first row, I say I have B, or I can go to E. Okay. So I select E. Remember, if the values are same, you can select whichever one at random. Typically, in the case of if you're implementing an algorithm here, I would have probably chosen B. I would say if two alphabets have the same value, choose the lowest one. Okay. So we start with city A and choose the closest city, in this case E. Okay. Now once we go to E, okay, we choose the closest city that has not yet been chosen. So you go to E. If you go at row E, right? So A and A is already, we started at A. We don't choose that. The next lowest value is cell E and C. So you choose C. Okay. So we get AEC. Now when you go to row C, then you choose the next lowest value, that is G. Okay, subject to the constraint. What is that constraint? Remember that bound, right? So kind of that we are heading there towards that. Cannot choose the same city because the whole path is you visit the node only once, right? Other than the starting city. So by following that, okay, so we know that the minimal tour will be no greater than this. You agree with that? That statement is an important statement. Okay? Because we already know a known way of doing it. A known way is the greedy method, right? We studied that. Always go to every node. Whatever branches you're getting out of that node, choose the lowest path. We did many problems on that. So that should be clear to you. Do you understand that? Saying that when I say the minimal tool will be no greater than that. Why do we say no greater than that? Because we have shown in the past that greedy method doesn't always work. Correct? We have shown plenty of examples saying, hey, greedy doesn't work. Even knapsack, greedy doesn't work. Where did we show those examples? When we did the chapter on dynamic programming, right? When we did dynamic programming, we said, if you think greedy always works, here are some examples where greedy doesn't work. That's why we chose dynamic programming, if you recall. Okay? Now, that is what the next sentence says. It's important to understand that the initial candidate tour is not necessarily a minimal tour, nor is it unique. Okay? So it turns out, if you start at city E, for example, okay, and you want to cover everything, you are going to get a length of 30. Okay, so there are different candidate tours with different values. Okay. Now, when you look at the candidate tour of E, A, B, H, C, D, F, D, E, would you choose that path or not? How do we determine that? We determine that by comparing, hey, is it a promising tour or not? How do we do that? We compare it with the best value that we have so far. The best value that we have so far is A, E, C, G, F, D, B, H, A, which is 28. So you eliminate the candidate tool, which goes E, A, B, H, C, G, F, D, E, because the value there is greater than the value that we already have. So the 28 is a better solution already. So why would I do the 30th? Unless By the way, who is doing this? Let's say this is Chakravarti Garu doing it at his desk, right? Visiting the colleges. Then he says, you know what could be a constraint, which of course he would not share with others, right? If you say, hey, you know what, in city E, I have my uncle or aunt, maybe I'll start there because I'll go there and then I'll spend a couple of days there, right? Then he might choose that. So whatever the constraints are, okay? If there are no constraints, typically if it is based on the values in the table that we have here, then obviously the candidate tool with 28 makes better sense. Okay. Okay, so this is an example of a bound. So we know what the bound is, because that is the important thing. The idea of using branch and bound is, the trick is to come up with the bound, right? If you do not know how to come up with a bound, then how do we use? Okay. So we have to figure out the heuristic. Okay. Let me pause here for a second. Any questions, comments? Faculty members, you want to add anything before I move on? An underestimate of the cost. Okay. Under meaning what could be the lowest estimate. Okay. So in this example, what he's doing is he's taking the actual cost to reach a node plus the minimum cost from every remaining node. Okay. So the heuristic Hx is equal to Ax, which is the actual cost to node X, and Gx is the minimum cost to complete the tour. Okay. And how do we compute Gx? Because we know the minimum cost from each node to anywhere. Apply that heuristic, right? Then you will see that the cost, the minimal tour cost cannot be less than 25. Okay. So when you are using that heuristic in this case, you see the minimal tour cost is 25. So you have a bound there again, right? You have a lower bound and then you have an upper bound, 25 and 28. Okay. How is he doing that, right? Here is a tree. Remember, that's why the trees are so important, right? Everything is done through a tree. So let's look at this picture here to find the minimal tour. What did he do? He said, hey, if I'm starting at A, how do you interpret this, right? After this, I'll give you, is there an example here next? Okay. Now let me finish this example and I'll give you a quick short break. Okay. So you start at node A, determine the actual cost to each of the other nodes. Okay. So we know what the cost of the nodes are, right? From A to B is 4. A to C is 7. Do you see that there on the previous slide somewhere? A to B is 4. See that first row, right? A to C is 7, A to D is 6. So you take A, make A as the root, and then you're doing that. Okay, you see the values 4, 7, 6, 4, 10, and all of those things. Okay. Now, if you make B as the next node, meaning you say, okay, I go through B. Now, from B, you compute, right, the minimum cost from every other node. Okay. So when you do from B, okay, now you say I have to cover rest of the nodes. You draw a branch like that again from B to rest of the nodes, minus the A to B, right? You get 21. Okay. And then in step 3, you add the actual cost to the node from A. So you are saying, pretend you are going from A to via B. You say, oh, from B to cover C, D, E, F, G, H, it's going to be 21. Plus A to B is 4. That's why next to B you see 25 value. That's how you came up with. Okay. Now, if you were to go from A to C, okay, you are going to get the total value as 28. And then 27 and so on. Okay. Now, step 4 is the critical step, guys. It's important for you to understand. Okay. supercritical, right? So when you look at 25, 28, 27, 25, 31, 29, 30, now you already know, based on the earlier analysis that I gave you, from the table, you know what the upper bound was, right? The candidate tour, if you look at this one here, that AEF, based on the greedy method, if you apply, you know AECGFDBHA gives you a tour length of 28, right? So we know that. Okay, so that means you're using your knowledge of the greedy method quickly, right? See how you're combining the ideas from different chapters here. So you're taking the knowledge of the greedy method, applying it, say, I already know my tour length cannot be more than 28. Now you're applying the branch, the bound statistic here. You're basically using that knowledge. You're building this tree. Now, since you know you cannot be better than 28, you can start pruning the branches. So when you prune the branches, what are you doing? Anything greater than 28, you eliminate because it is less than or equal to, right? So greater than 28 is what? Going from A to F. So when you prune that, you are left with B, D, and E, highlighted in a different color, right? So once you get the promising notes, B, D, and E, those are the only things that you expand. Did we save time to figure out what is the best way to do that by pruning the notes? In the case of backtracking, when you did one, you completed almost like an exhaustive search in backtracking. You traversed all the notes, all the branches. So whereas by putting a bound, by knowing what that bound is, we did not have to go depth all the way from C, whatever depth of the tree it comes. So we eliminated those things. So we have saved traversal like in backtracking. So eliminating means that saves time, right? So more efficient way of doing it. That's what it boils down to. Okay. Now, recursively apply the same problem, and then you come up with a solution. So you selected, it turns out of all these things, you selected the lowest cost. By default, it will be lowest cost, right? Because the upper bound, we are at every level, you're taking the, is it less than the 28 value, total value. So at every stage, you're looking at the promising node, taking the lowest cost there out of them. Breadth first, search, and then once you selected the node at the breadth, then you go deep. Okay. Okay. Questions on that? It's a very beautiful algorithm, by the way. I love branch and bound tech of a bound. How to come up with a bound, right? There is no right or wrong way, by the way. In this case, he came up with some heuristic. What is a heuristic? How do you define a heuristic? Can somebody tell me what a heuristic is? I think I should have defined it. When we say heuristic, what do we mean by that? Faculty members, you are welcome to put the answer for that, for the benefit of the students. When we say heuristic, what do we mean by that? Since we did the candidate tour using greedy method, that because we know that's a heuristic, right? We said, I know that the upper bound, it cannot be greater than 28. So I use that knowledge practically because I know that I can apply that, right? Greedy method quickly, I can arrive at the upper bound quickly. Okay. And then I started using that knowledge to prune non-promising or unpromising branches. to arrive at the final solution. Okay. Give me a second, guys. Using that logic. Okay. A lot of slides there. Okay. So what did you come up with the final analysis? Let me check. Give me a second. Move the chat window. Branch and bound, right? Ultimately, he came up with a tour length which has to be greater than or equal to 28. And then we know that the candidate tour now has a length of 28. So we know that it's a minimal tour and we use it without searching the state space tree, as long as you covered all the nodes. Okay. By using the bound of 28, we are able to come up with the solution without having to traverse all branches of the tree. That's what the algorithm basically is. Okay. Now, here is another example. I think I'll make you do it as a group exercise now, right? Let's see that. What does it say here? In the previous example, the initial candidate tour turns out to be a minimal tour. Okay. We lucked out. Okay. So now we are saying that let's take another tour which is not a minimal tour. Okay. So let's look at that one. The initial tour is AFEDBCA with a tour length of 32. Of leaving every node is 29. So we know that we cannot. We know the minimal tour cannot have a length less than 29. Okay. So how do you come up from this analysis, right? Initially our candidate tour was 28, we lucked out. But if we take some other initial tour, because we don't know how he came up with some initial tour, remember, it's a best guess, right? Probably they didn't apply the greedy method. They applied some other technique. They came up with some initial tour, which is AFEDBCA, and the tour length is 32. Okay. And I already know the minimum cost of leaving every node is 29. So based on that, we say, okay, maximum length should be 29. So you're drawing the branches there for the tour from A to F, A to B, A to C, D, E, F, A, B, C, D, E, F here, right? The heuristic is, if you look at H of AB, okay, is that two things from A to B distance plus the rest of the distance, right? 25 plus 8, I don't know why I added a 32. I think there's one small typo there in arithmetic. It could be 25 plus 7 maybe. You verify that. I remember I had some small mistake there in addition. Okay. Now, then you say what are the possible live nodes? What is the concept of live node meaning? The nodes that we can consider further, right? Are C, F, and E. Why did we say C, E, F, and E? They're colored in purple, right? Because equal to C, F, and E. They are better. They have better solutions than 32. Okay, that's what it is, right? Because initial tour is AFEDBCA, which is length of 32. Okay, but if you look at the other nodes, the solution is better than 32. So you select the live nodes, and then you build a tree again, as we discussed. Okay. So that concept of live node list, basically we're using the bounding value. And then of course by the level of completion, right? And again, when the values are same, we place one that is closer to the completion ahead of the other node. Okay. Because when you are using that approximation, you see that value, the bounding value of the node closer to completion is more likely to be closer to the actual tool length. So that is where the practical knowledge is applied. And then you build a tree and then you come up with the tool length. So the way you came up with the tool length, you can see how it has been highlighted. Okay. So you can I give you more examples of which nodes are expanded. You'll review that. The reason is I covered one branch and bound tree completely. So this one I'm kind of like glossing over because I want you to review that and trace it yourself. But then the slide is there to help you. Okay. Okay. So going along the way, we'll actually see. 1 second. 1 second, convince yourself how this leads to another path. Okay. Okay. This is what I wanted to get to, right, today? Your group exercise. Okay. So you have a graph. This is what you'll do the rest of the class. What is the time now? Yeah, just enough time to do this, right? So far you learned theory. Now you will apply it. Okay. So you select a starting point. It can be anything. Okay. Determine a candidate tool from your starting point. Okay. Whatever I showed you is what you'll do. I'm saying you choose a greedy method. Okay. Now, when you do the greedy method, whatever you get, you keep that aside, and then you have to draw all the paired distance matrix. Okay, like how I am showing here, right? I did not give you the table per se. So A to B is 3 in the above graph, right? Yeah, A to B is 3. So you figure out how to build that table. Okay. That is the third bullet. Come up with a bounding heuristic, which I gave you, right? And then once you come up with the bounding heuristic, that formula that I gave you, right, on slide 10. I don't know why it said 10. I didn't even keep track of the number slide here, but let's look at it. Where is the bounding heuristic here? Give me a second. This is one. I'm going to talk about a bounding heuristic, right? Hx equal to Ax plus Gx. Ax is actual cost to node X and Gx is minimum cost to complete. Okay? Okay? And then you have to apply the concepts to come up with the traveling salesman problem branches as we discussed. Okay? Let me show you what we have done. I give you the solution there as to how to do it, but in your case, you do it first and then refer to the solution. Okay. Initially, it was an exercise in the class, and then later I think I changed it to a group exercise. But I want you to follow this, whatever I'm showing here, as an exercise to understand how this was obtained based on the concepts that we have done. Okay, so I'm giving you like tracing of the code, right? Your goal is to understand that. Okay, now I'm going to post it in the next minute or so for you to figure that out. Then that's all I will teach today, because the next one is going to be getting into the knapsack problem, right? So we can do that in the next class. Let me post this one here. The goal is, this is the picture. Okay. Actually, I'll leave it like that even before I post it in the community, right? So you take the node on the left, okay, pencils and papers out. Write down the graph on the left that I gave you. E, B, C, D, E, and the numbers there. Okay. If you can draw that one picture, which I show you on the left, right? Because on the previous slide that got cut off, right? This picture on the top kind of got cut off. Okay. So from that, you build a table as it says here. Okay. Come up with a candidate tool. Again, you can make any starting point. It doesn't matter whether it's A or B or C, D or E. Okay. The goal is the tool should cover all the nodes. Okay. And then come up with a bounding heuristic, as I mentioned, and then solve the problem. Trace the tree. That is what the exercise is. Okay. Anyone has any questions on that? Okay. So in the remaining time, I want you to do the exercise, and then let me post it. Actually, you do value for P2A also. So build that matrix. Very easy to build that matrix. When I say matrix, the table that I'm showing you here. Okay. I've already given you the graph on the top, right? So build that matrix. Okay. In that matrix, you're basically drawing the bound. I want you to come up with a bounding heuristic, which is hx equal to ax plus gx, and I gave you the cost to the node, right? Now you're doing that bound heuristic based on what? Based on the candidate tool here, right? Whatever candidate tool you have chosen. That is important to remember, bullet 2, right? So once you have the bound heuristic, okay, now you apply our concepts. What are the concepts that I said you are applying? If you go back here, I'll explain to you the main concept, then you can do that, right? You have the heuristic, right? Then you are applying this concept here. So when I say A was my candidate to starting point, okay? That's why I started A. Now you will compute the minimum cost to every other node, okay? And then you're writing down what the total cost is going to be, okay? Now, which of the question that we're trying to solve is, which of the nodes are promising to explore further? That is what we are trying to do in branch and bound, right? So do I explore B, do I explore C, D, E, F, G, H in this case? And to answer that question, I'm looking at the values. Like if you see the 25, 28, 27 and all that, we are saying, hey, is that better than the heuristic? It cannot be greater than the heuristic, right? Because you chose a candidate tool, you already know the upper bound. So you mark the promising nodes. Now out of the promising nodes, you select the lowest value. Okay, that is what the heuristic is doing here. Okay. So if you see, that's the other concept, right? You take the lowest value, in this case E was 25, okay? And then you again, from there, you mark to the remaining nodes. If you see from E, what are the remaining nodes? B, C, D, F, G, H. You do not count the branch to A because you have already selected A. A and E are done. So out of the remaining nodes, you draw the branch, you compute the cost again, and then repeat that cycle. So that is the exercise in the remaining time, and also outside of the time. I don't think you'll finish that exercise in the remaining time. So a little bit of class time, since we started a little bit late. If you can hang on in the class for another 10-15 minutes, if you don't have other classes, work on this exercise and then continue that exercise. Okay? Let me see. Any questions, comments as to what you need to do?